Every detail in this story comes from real scientific research and observation. There is a moon in our solar system larger than the planet Mercury. It has its own magnetic field. No other moon in the solar system can say that. Beneath its surface, beneath 150 kilometers of silence and ice, there is an ocean. Not a small one. The water locked inside this single moon is estimated to be 25 to 35 times the volume of every ocean on Earth combined. It has been there for billions of years, and no one has ever seen it. Tonight, you are going there. You will cross the boundary of Jupiter's magnetic field, a region so vast it would be visible to the naked eye from Earth if it could be seen. You will watch auroras bend, not because of solar wind alone, because something underneath the ice is conducting electricity. Something liquid, something ancient. You will stand on a surface that has not changed in 3 billion years. Dark terrain, cratered and silent, pressed up against pale grooved ridges that formed when this world was still young enough to move. A surface that remembers a time before Earth had continents. In 1610, a man pointed a handmade telescope at Jupiter and saw 4 small points of light that should not have been there. He watched them move, night after night. He understood, slowly, that they were orbiting something other than Earth. That moment broke the model of the universe that humanity had held for over 1,000 years. One of those points of light was this moon. Tonight you are not looking at a point of light. You are already here, floating above a world 5,268 kilometers across, larger than Mercury, larger than Pluto, large enough that if it orbited the Sun instead of Jupiter, it would be classified as a planet without hesitation, and yet it circles a gas giant 1,070,400 kilometers away, locked in a gravitational rhythm so precise it has not missed a single beat in billions of years. You will descend through terrain that last moved 2 billion years ago. You will pass over a crater 585 kilometers wide, the scar left by a rock that hit this surface with the energy of billions of nuclear weapons and left nothing but silence behind. You will learn that a spacecraft called Galileo, orbiting Jupiter in the late 1990s, crossed into Ganymede's magnetic field and came out the other side changed, its instruments recording a boundary that no one had expected to find around a moon. You will understand why the largest moon in the solar system is also the strangest. And at some point, without knowing exactly when it happened, you will be asleep. You are about to go down. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Ganymede is the largest moon in the solar system, and it is larger than a planet. Its diameter of 5,268 kilometers exceeds that of Mercury by more than 2%, and it exceeds Pluto by nearly half. If Ganymede orbited the Sun directly instead of orbiting Jupiter, there would be no debate. It would be called a planet. But it does not orbit the Sun. It orbits Jupiter at a mean distance of approximately 1,070,400 kilometers, completing one full revolution every 7 Earth days and 3 hours. It is locked in what astronomers call the Laplace resonance, a gravitational relationship so mathematically exact that for every one orbit Ganymede completes around Jupiter, Europa completes exactly 2, and Io completes exactly 4. This resonance has held, without deviation, for billions of years. Tonight, you are approaching this world. You have crossed the outer boundaries of the Jovian system, the region of space dominated by Jupiter's gravity, a sphere of influence extending more than 48 million kilometers in every direction. Jupiter itself is now visible off to your left, an enormous banded sphere, its great red spot, a permanent storm larger than Earth, its cloud layers moving in opposite directions at wind speeds exceeding 600 kilometers per hour. But you are not going to Jupiter. You are going to the largest thing orbiting it. Ahead of you, Ganymede is resolving from a disk into a world. You are close enough now to see color. You are close enough now to see texture. You slow your approach and let the moon fill your field of vision. What you see is not what you expected. It is not uniform. It is not a single color or a single surface. Ganymede is divided, visibly, strikingly, into 2 completely different kinds of terrain, and the boundary between them is one of the most scientifically significant geological features in the outer solar system. Roughly 1/3 of Ganymede's surface is dark. Ancient dark. A deep brownish gray that absorbs light rather than reflecting it, covered in impact craters, so numerous and so dense that counting them individually would be an act of patience beyond reason. This is the oldest terrain on Ganymede. Scientists call it ancient dark terrain, and some of its regions have specific names, Galileo Regio being the largest, spanning roughly 4,000 kilometers across. The crater density in these dark regions tells a story in the language of physics. The more craters a surface has, the longer it has been exposed to the bombardment of space. These dark plains have been receiving impacts for approximately 4 billion years. They predate the formation of Earth's continents. They predate multicellular life on Earth. They are, in geological terms, almost as old as the solar system itself. You descend lower, letting the curvature of Ganymede drop away on either side as the surface rises toward you. The dark terrain below is textured in ways that become clearer as you approach. There are craters within craters. Smaller impacts inside older ones, the chronological record of 4 billion years of bombardment written in stone and ice. Some craters show a feature called palimpsests, shallow, ghostly circular depressions where an ancient crater once existed, but where the surface has slowly relaxed over geological time, the ice creeping inward over millions of years until the original depth is mostly gone, but the circular outline remains, faint as a watermark. Palimpsests exist because Ganymede's surface is not pure rock. It is a mixture, roughly half silicate rock and half water ice, and ice, over geological timescales, behaves less like a rigid solid and more like an extraordinarily slow-moving fluid. A crater that formed 3 billion years ago in pure rock would look almost identical today. A crater that formed 3 billion years ago in a mixture of rock and ice has had 3 billion years to soften, to settle, to flatten out at the edges and blur at the center. The palimpsests you can see below you are craters that have been slowly forgetting themselves for billions of years. You move across the terminator, the line between Ganymede's sunlit hemisphere and its shadow, and the low angle of the sunlight does something extraordinary to the surface. It rakes across the terrain at a nearly horizontal angle, and in that light, the texture of the ancient dark plains becomes three-dimensional, every subtle ridge and depression throwing a long, thin shadow. You can see now that the dark terrain is not flat. It undulates. There are low ridges running across it in directions that seem almost arbitrary, ancient features from a time so early in Ganymede's history that the processes that formed them are no longer active. Among the most striking surface features in the ancient dark terrain are the impact craters that show a distinct three-ring structure called multi-ring basins. These formed when ancient impactors struck with sufficient energy to cause the crust to respond, not just at the point of impact, but in concentric waves outward, like rings spreading across the surface of still water when a stone is dropped into it. On Ganymede, the icy composition of the crust allowed those waves to propagate further than they would in pure silicate rock, and the rings froze in place as the crust quickly resolidified after the impact energy dissipated. The largest such feature on Ganymede is Gilgamesh Basin, a multi-ring impact structure in the southern hemisphere approximately 585 kilometers in diameter, with concentric ridges extending outward from a central depression that has been partially filled by later geological activity. Gilgamesh formed during the period of intense bombardment early in the solar system's history, and its scale speaks to the size of the impactor that created it. An object likely tens of kilometers across, moving at tens of kilometers per second, releasing energy equivalent to billions of nuclear weapons in a fraction of a second. The basin has been quiet ever since. You look at it from altitude, the concentric rings, subtle under the raking sunlight, the central plane smooth where ancient material welled up from the warm interior to fill the deepest part of the wound. 3.5 billion years of stillness. And then, at the edge of the dark terrain, the surface changes. Completely. The transition is sharp enough to seem almost geologically violent in its clarity. The dark, heavily cratered ancient plains end, and something different begins, lighter in color, more reflective, and marked not by the random distribution of impact craters, but by long parallel grooves and ridges running in sweeping arcs across the surface. This is Ganymede's grooved terrain. Scientists call the individual groove systems sulci, a Latin word meaning furrows, and they cover approximately 2/3 of Ganymede's surface. The sulci are extraordinary. Some groove systems run for thousands of kilometers in nearly straight lines. Others curve across the surface in broad sweeping arcs. The individual grooves within a system are typically between 1 and 2 kilometers wide, and the ridges between them rise only a few hundred meters above the adjacent valleys, gentle by mountain standards, but unmistakable from altitude. The grooved terrain is brighter than the ancient dark terrain. Its albedo, the fraction of incoming sunlight it reflects back into space, is measurably higher because the grooved terrain is fresher. Not fresh in any human sense of the word. The grooved terrain formed between roughly 1.5 billion and 3 billion years ago. but compared to the 4 billion-year-old dark plains, it is almost young. The grooves formed because Ganymede, early in its history, experienced a period of significant internal activity. Something inside this moon was generating enough heat to cause the outer crust to stretch and fracture. Old, dark, densely cratered crust was pulled apart along fault lines, and fresher, lighter material from beneath welled up to fill the gaps. The process is similar in some ways to the tectonic rifting that creates rift valleys on Earth, the East African rift being a modern example, but on Ganymede, it was driven by the gravitational forces of Jupiter and the other Galilean moons heating the interior through tidal flexing rather than by mantle convection alone. Within the grooved terrain, individual sulci have been named by the International Astronomical Union using mythological terminology. Uruk Sulcus is one of the best studied groove systems, a long, bright region of parallel grooves and ridges, imaged in detail by the Galileo spacecraft during multiple close flybys in the late 1990s. The imagery from those flybys revealed that the individual parallel ridges and troughs show evidence of having formed by extension, the crust being pulled apart, rather than by compression. This is significant because it suggests that during the active phase of grooved terrain formation, Ganymede's total surface area was actually increasing. Old crust was being stretched and thinned. New material was being added from below. The surface of Ganymede was growing. This process eventually stopped. The internal heat source that was driving the extensional tectonics cooled or diminished, the crust thickened and stiffened, and the period of geological activity ended. Since then, for the past 1.5 to 2 billion years, Ganymede's surface has been geologically quiet. No new grooves have formed. No new dark terrain has been exposed. The surface you are looking at now is essentially the surface as it has been for the past 2 billion years, modified only by the steady rain of micrometeorites and occasional larger impactors that have slowly added to the crater count and gradually darkened the bright grooved terrain through a process called space weathering. You hover above the boundary between the dark and grooved terrains and look along it. It runs for hundreds of kilometers in either direction. On one side, 4 billion years of silence, bombardment, and slow icy creep. On the other, evidence of a world that once moved, that once had something happening inside it, that once had geological youth. This boundary is, in a sense, the most dramatic geological contact zone in the outer solar system. Below you, partially buried at the base of the slope where the old terrain meets the new, there is a large impact crater. Its rim intersects the boundary between the dark and grooved terrain, which means it formed after both surfaces already existed. The crater is a clock. Its position tells you that whatever process created the groove system had already finished before this particular rock hit the surface. Ganymede records time in craters. The surface is a stratigraphic record, as legible to planetary scientists as tree rings are to a botanist. The sun from this distance is not the dominant light source it is on Earth. Jupiter is, at its current orbital position, approximately 778 million kilometers from the Sun. At that distance, the Sun appears as an extremely bright star, intense enough to cause damage if you looked at it directly, but only about 1/27th as bright as it appears from Earth. The light that falls on Ganymede's surface is thin and cold. The surface temperature on the sunlit side is approximately minus 113 degrees Celsius. On the night side, it drops to approximately minus 183 degrees Celsius. At those temperatures, the water ice that makes up roughly half of Ganymede's surface is hard and brittle as stone, and it has been that way for billions of years. You set down gently on the grooved terrain. You are standing on the surface of the largest moon in the solar system. The ground beneath your feet is a mixture of silicate rock and water ice, compressed and cold, solid as granite at this temperature, and it has not changed in approximately 3 billion years. The grooves stretch out in front of you, long, parallel ridges running off toward the horizon, which is close, noticeably closer than it would be on Earth, because Ganymede is smaller and the curvature of the surface is sharper. On Earth, standing in a flat, open space, the horizon is approximately 4.5 kilometers away. On Ganymede, it is closer to 3. Jupiter hangs in the sky above the horizon. Enormous. Impossible in its scale. Its disk spans an angular diameter of nearly 8 degrees as seen from Ganymede's surface. For comparison, the full moon from Earth spans about half a degree. Jupiter from Ganymede's surface is roughly 15 times wider than the moon appears from Earth. It fills a significant portion of the sky, and it is banded, the parallel cloud belts running in alternating shades of orange, cream, brown, and tan, the boundaries between them sheared by wind speeds that have no equivalent on any rocky planet. Jupiter's 4 large moons, the Galilean moons, were discovered by Galileo Galilei in January of 1610 using a telescope he had built himself. His telescope had a magnification of about 20 times. He noticed, on the night of January 7th, 3 small stars arranged in a line near Jupiter, and he noted that their position relative to the planet was unusual. The following nights, he observed them again. They moved. But they moved in a pattern. They stayed near Jupiter. They appeared on one side and then the other. They changed configuration but always remained close to the giant planet. By January 13th, he had observed a 4th point of light. He concluded, correctly, that these were objects orbiting Jupiter. This was profoundly significant. In the prevailing model of the cosmos at the time, the Ptolemaic model, everything in the sky orbited Earth. These 4 points of light clearly did not. This was among the earliest direct observational evidence that not everything in the cosmos moved around Earth, a piece of data that contributed, along with many others, to the eventual acceptance of the heliocentric model. The moon you are standing on now was one of those 4 points of light. Galileo named the 4 moons the Medicean stars, after the powerful Medici family of Florence, whose patronage he was seeking. Later astronomers gave them the names we use today: Io, Europa, Ganymede, and Callisto, drawn from Greek mythology. Ganymede was the cupbearer of the gods on Mount Olympus, described in mythology as the most beautiful of mortals, carried to Olympus by Zeus, who in the Roman tradition is Jupiter. The name is appropriate in ways the ancient Greeks could not have imagined. You stand on the surface and look up at the banded giant in the sky. The Laplace resonance that governs Ganymede's orbit is not merely a mathematical coincidence. It has physical consequences. Every time Ganymede completes one orbit around Jupiter, Europa has completed exactly 2, and Io has completed exactly 4. This means that these 3 moons regularly align, periodically finding themselves in a straight line, each one pulling gravitationally on the others in a repeating, synchronized pattern. The gravitational tugs from this resonance do not significantly alter Ganymede's orbit, but they do something important to its interior. The slight eccentricity maintained in Ganymede's orbit, the slight deviation from a perfect circle sustained by the resonance, means that Jupiter's gravitational pull on Ganymede is not perfectly constant. As Ganymede moves slightly closer to Jupiter and then slightly farther away in each orbit, Jupiter's tidal force stretches and relaxes the Moon. The effect is analogous to repeatedly bending a piece of metal. Energy is deposited in the material. In Ganymede's case, that energy goes into the interior, generating heat. Not a great deal of heat compared to what Io receives. Io is closest to Jupiter and experiences the most intense tidal flexing, which is why Io is the most volcanically active body in the solar system. Ganymede's tidal heating is considerably more modest, but it is not zero. And over billions of years, even modest tidal heating accumulates. You look down at the ground beneath your feet and think about what modest means at geological timescales. The surface is still. The temperature is still minus 113 degrees on this side. Jupiter's light, reflected off its cloud tops, supplements the thin sunlight, casting a faint amber-tinged glow across the grooved terrain. There is no wind. There is almost no atmosphere. Ganymede has an exosphere composed primarily of oxygen and small amounts of ozone, but it is so sparse, with a surface pressure roughly 10 trillion times lower than Earth's sea level pressure, that it does not move air from place to place. It does not carry sound. It cannot be felt. There is only the cold and the silence and the enormous planet above you and the slow rhythmic gravitational pull of the Laplace resonance, ticking with the mathematical precision of a clock that has been running for 4.5 billion years. The oxygen in Ganymede's exosphere is produced by radiolysis, the breaking apart of water ice molecules on the surface by high-energy charged particles from Jupiter's radiation environment. When an energetic particle from Jupiter's magnetosphere strikes a water molecule frozen into Ganymede's surface, it can break the molecular bond between the hydrogen and oxygen atoms. The lighter hydrogen atoms escape to space more easily, while the heavier oxygen atoms are more likely to remain, slowly building up a tenuous population of oxygen molecules at the surface. The same process produces ozone, a molecule made of 3 oxygen atoms, which has also been detected in Ganymede's exosphere by ultraviolet spectroscopy. This is not a life-supporting atmosphere. It is physics. It is the slow, mechanical consequence of being a world made partly of ice, orbiting a planet surrounded by an intense radiation environment, exposed over billions of years. The surface beneath you holds more than ice and rock. Spectroscopic measurements from the Galileo spacecraft and from Earth-based telescopes have detected carbon dioxide ice, sulfur dioxide, and various hydrated minerals, compounds that formed through the interaction of the surface material with the charged particle radiation from Jupiter's magnetosphere, accumulated over billions of years of exposure. The dark terrain in particular has a higher concentration of non-ice materials than the grooved terrain. Its darker color is not simply a matter of age. It is a matter of chemistry, of what happens to a mixed surface of ice and silicate rock when it is irradiated for 4 billion years. The radiation breaks molecular bonds, rearranges atoms, polymerizes organic compounds into dark, complex macromolecules, similar in some ways to the tholins found on the surfaces of outer solar system bodies. The result is a surface that is darker than fresh ice, more chemically complex than either pure rock or pure ice, and still actively being modified today by the same radiation that has been working on it since the beginning of the solar system. The named features on Ganymede's surface reflect the mythological theme established by the moon's own name. In the Ptolemaic tradition, Ganymede, the cupbearer of the Olympian gods, connected this world to the divine. And so the craters of Ganymede carry names from mythology and ancient history: Osiris, Gilgamesh, Tros, and Ketu, Melkart. The groove systems, the sulci, carry names from ancient places: Uruk Sulcus, named for the ancient Mesopotamian city of Uruk, one of the oldest cities in human history. Nippur Sulcus, named for another ancient Sumerian city. Harpagia Sulcus, from classical mythology. The nomenclature is a reminder that the study of Ganymede is not purely a modern enterprise. The humans who named these ancient cities had no concept of the moon that would one day carry their cities' names. They built their ziggurats, recorded their astronomical observations on clay tablets, and mapped the visible sky with the instruments available to them. The sky they mapped included Jupiter, which they knew as Marduk, the chief deity of the Babylonian pantheon. And near Marduk in the sky, on certain nights, a faint point of light that no one understood yet, that no telescope could yet resolve, that was in fact a world of 5,268 kilometers diameter, with its own magnetic field and a buried ocean larger than all of Earth's seas. That connection, from ancient Uruk to modern planetary science, is not a short one. It is the full length of recorded human history. You stand on a ridge of Uruk Sulcus and think about that. The groove beneath you formed approximately 2 billion years ago, before writing existed, before cities existed, before any human had ever stood anywhere and looked up at a sky and wondered about the points of light in it. The ridge will still be here, unchanged, when the last human city has been forgotten. Ganymede does not keep human time. It keeps geological time, and the difference is so large it is difficult to hold clearly in the mind. The surface is still. The stars are fixed. Jupiter does not acknowledge your presence. The groove extends away from you in both directions, parallel to a dozen other grooves, all of them carved by the same extensional forces that operated here 2 billion years ago and then stopped, leaving this record, leaving this writing in ice, which you are now reading. Io is somewhere over the horizon right now, completing another orbit. Europa is in its own position, waterlocked beneath an ice shell of its own. And the three of them, Io, Europa, Ganymede, are bound together in their resonance, and Jupiter is pulling all three, and this has been happening since before the Earth had a moon. You sit down on the ridged surface of the grooved terrain. The ridge beneath you is cold but solid. The groove beside you drops perhaps 200 meters before flattening out into a smooth valley floor, and the far wall of the groove rises again in a gentle slope a kilometer away. The scale is geological. The time is geological. And yet here you are at the boundary between terrain that formed 4 billion years ago and terrain that formed 3 billion years ago, with Jupiter filling the sky and the Laplace resonance keeping time below you like a heartbeat this moon has been living by since before there was life on Earth. Something is happening beneath you. Something the surface does not show. You cannot see it from here. No one can see it from the surface, but the instruments that have passed by this world and the telescope that orbited Earth over 1 billion kilometers away have measured something that should not be here. A magnetic field. Ganymede has its own magnetic field, not borrowed from Jupiter. Not an induced effect of the Jovian magnetosphere pressing against a conducting layer beneath the surface. Its own internally generated, self-sustaining magnetic field. No other moon in the solar system has this. Not Titan, not Europa, not Callisto, not Io, not any of the hundreds of smaller moons orbiting the gas giants. Only Ganymede. And the question of why, the question of what is happening inside this world to generate and sustain a magnetic field, leads directly downward through 150 kilometers of ice into a place no spacecraft has ever reached. You look down at the ground beneath your hands. The ice is cold and still and silent. But something beneath it is moving. Something beneath it has been moving for a very long time. You remain seated on the ridge for a moment longer. Jupiter turns slowly above you, its cloud bands shifting over the course of hours, its great red spot, a storm that has persisted for at least 350 years of observation and likely far longer, rotating around toward the limb and out of view. The grooves stretch out on either side of you, ancient and quiet. The dark terrain off to your left is darker now in the low amber light, its craters softened by shadow. The exosphere above you is invisible, undetectable by any human sense. And below the ground, below the rock and ice and the deep structural layers of this differentiated world, something is generating a magnetic field, creating an invisible architecture that hangs above the surface of this moon like a shell carved out from Jupiter's overwhelming field, kept open by whatever is happening in the deep interior. It has been there for what scientists believe may be billions of years. And tonight you are going to cross into it. You are going to step up off this surface and rise through the thin exosphere and into the space where Ganymede's magnetic field begins to push back against Jupiter's. The ground is solid beneath you. Jupiter is immense above you. The Laplace resonance keeps its perfect time. And somewhere far above the surface, invisible and ancient and electrically alive, Ganymede's magnetosphere is waiting. You push yourself to your feet. You rise. The surface falls away below you as you ascend through the exosphere, which thins and then is simply gone, and you are in open space above Ganymede, the grooved terrain curving away in every direction below you, the dark terrain of Galileo Regio, visible as a broad dark patch to your left, and ahead of you and above you, the structure of space is about to change. You are rising into the magnetic field. Something is different about the space here. Something is ordered. Something has been organized. The magnetic field of Ganymede, generated deep inside this moon, maintained by processes still being actively investigated by planetary scientists, extends outward from the surface and forms a region called a magnetosphere, a volume of space within which Ganymede's internal magnetic field is the dominant influence on charged particles. But Ganymede's magnetosphere does not exist in empty space. It exists inside Jupiter's magnetosphere. And that changes everything about what it looks like. Jupiter's magnetosphere is the largest structure in the solar system. Larger than the Sun? If Jupiter's magnetosphere were visible to the naked eye from Earth, it would appear several times larger than the full moon in the sky. It extends outward from Jupiter for approximately 3 to 7 million kilometers on the sunward side, and it stretches into a magnetotail on the opposite side that extends for hundreds of millions of kilometers past the orbit of Saturn. Ganymede orbits inside this structure, and inside that vast Jovian magnetosphere, Ganymede's own magnetic field carves out a small protected region, a magnetosphere within a magnetosphere, a bubble of Ganymede's own magnetic influence, roughly 2.6 times the radius of Ganymede itself in extent. You rise through the outer boundary of this bubble, the magnetobause, where Ganymede's field pressure equals Jupiter's field pressure, and you cross into a different regime. Outside this boundary, the charged particles moving through space are Jupiter's ions and electrons swept up by the Jovian magnetosphere, moving at the velocities and in the directions determined by Jupiter's 10-hour rotation. Inside this boundary, Ganymede's field takes over. The particles here move differently. The field lines here curve back toward Ganymede's poles, following the geometry of a dipole magnetic field, the same fundamental geometry as Earth's magnetic field, with a north magnetic pole and a south magnetic pole, and field lines arcing from one to the other through space. Ganymede's magnetic field is tilted about 176 degrees from its orbital axis, which means it is roughly anti-aligned with Jupiter's magnetic field. This misalignment creates a dynamic tension at the magnetopause. The boundary between the two fields is not a smooth wall. It is turbulent and complex. Reconnection events, moments when opposing field lines from the two magnetospheres touch and reconfigure, produce bursts of energetic particles that travel down the field lines toward Ganymede's polar regions. And when those particles hit the thin oxygen exosphere near the poles, they produce light. They produce auroras. Not the red and green auroras of Earth, produced at visible wavelengths by excited nitrogen and oxygen molecules in a dense atmosphere. Ganymede's auroras emit primarily in the ultraviolet. They are invisible to human eyes. But the Hubble Space Telescope, pointed at Ganymede from its orbit around Earth, can detect ultraviolet emissions. And in 2015, a team of scientists led by Joachim Sauer of the University of Cologne used the Hubble Space Telescope's Space Telescope Imaging Spectrograph to observe Ganymede's auroral bands over the course of a full orbital period. They were not primarily looking for auroras. They were using the auroras as a tool. Here is the logic. Ganymede's auroral bands, the glowing ultraviolet rings centered on the magnetic poles, are located at specific latitudes determined by the geometry of the magnetic field. The position of the auroral bands rocks back and forth slightly as Ganymede moves through different regions of Jupiter's vast magnetosphere. The amplitude of that rocking depends on the electrical conductivity of the material beneath Ganymede's surface. If the interior beneath the ice were simply rock and ice with no conductive layer, the auroral bands would rock by a predicted amount. If there were a layer of electrically conductive fluid, specifically a saltwater ocean, beneath the ice, the induced magnetic field from that conducting layer would partially dampen the rocking. The ocean would act as a brake. Soar's team measured the rocking. They found it to be about 2 degrees of latitude. The models predicted 6 degrees if there were no subsurface ocean. The observed rocking of 2 degrees was consistent with, and best explained by, the presence of a saltwater ocean beneath Ganymede's icy surface, an ocean whose dissolved salts make it electrically conductive enough to partially shield the aurora from Jupiter's varying magnetic influence. This is one of the most elegant pieces of indirect evidence in modern planetary science. An ocean, never seen, never directly sampled, 150 kilometers beneath the surface, revealed by the way it subtly dampens the motion of auroral light, visible from a telescope orbiting Earth. You are above Ganymede's north polar region now, looking down toward the aurora. You cannot see it with your eyes. It is ultraviolet light, beyond the range of human vision. But if you could see it, it would appear as a broad ring of glowing light centered on the magnetic North Pole, roughly following a circle of latitude, shimmering with the faint but constant bombardment of charged particles streaming down along the field lines. The aurora ring is not perfectly steady. It moves. Slowly, over the course of Ganymede's 7-day orbit, the ring rocks back and forth by about 2 degrees of latitude, dampened by 100 billion tons of salt water, more than 150 kilometers beneath the ice. The ocean is not passive. Its electrical conductivity means that as Jupiter's magnetic field changes, driven by Jupiter's 10-hour rotation, currents are induced in the ocean. The ocean responds. The ocean pushes back. The ocean leaves its fingerprints on the aurora. The mechanism of induction is the same basic physics that governs how an electrical generator works. A conducting loop moved through a changing magnetic field generates a current. The current generates its own magnetic field. That induced magnetic field partially opposes the change in the external field. It acts as a brake, as a moderating influence. If the conductive layer is a deep global saltwater ocean, the induced currents are large, and the braking effect is significant. If there is no conductive layer, there is no induction and no braking. The difference in aurora rocking between these two cases is measurable. It was measured. 2 degrees, not 6. The ocean is there. Ganymede's magnetic field strength at its surface is approximately 720 nanoteslas at the equator. For reference, Earth's magnetic field at the equator is approximately 30,000 nanoteslas. Ganymede's field is about 1/40th as strong as Earth's. But it is generated by the same basic mechanism, a liquid iron-rich core undergoing convective motion with the movement of electrically conducting fluid generating and sustaining a magnetic field through a process called a geodynamo. On Earth, the geodynamo is driven by a combination of thermal convection, heat escaping from the inner core driving circulation in the outer liquid core, and compositional convection driven by the solidification of iron at the inner core boundary, releasing lighter elements that rise buoyantly through the liquid outer core. On Ganymede, the details of the geodynamo are less well understood. The core radius is estimated to be approximately 800 kilometers, roughly 30% of Ganymede's total radius. It is believed to be iron or iron sulfide, partially liquid. The convective motion in this liquid iron core generates and sustains the magnetic field. But the precise energy budget that keeps this core in a convecting, dynamo-sustaining state, rather than having cooled and solidified, which would shut down the dynamo, is still an open question in planetary science. Tidal heating from the Laplace resonance contributes some heat to the interior. Radioactive decay of long-lived isotopes, uranium, thorium, potassium-40, contributes additional heat over geological time. The combination of these heat sources has apparently been sufficient to maintain a partially liquid core and a functioning geodynamo for billions of years. And that geodynamo protects Ganymede in a way nothing else in the outer solar system is protected. Jupiter's radiation environment is extreme. Jupiter's magnetosphere is filled with charged particles, protons and electrons trapped in the magnetic field, accelerated to high energies, circulating through the Jovian system. The radiation flux at Ganymede's orbital distance is high enough that an unprotected human would receive a lethal radiation dose within hours. Ganymede's magnetosphere changes the calculation. The magnetopause deflects a substantial fraction of the energetic particles from Jupiter's magnetosphere, at least at low latitudes. The equatorial and mid-latitude regions of Ganymede's surface experience significantly lower radiation fluxes than they would without the magnetosphere. The polar regions, where the field lines are open and particles can funnel in, receive more radiation, which is precisely why the auroras form at the poles. The polar regions of Ganymede show distinctive surface coloration in ultraviolet observations, darker, more processed material consistent with intense radiation bombardment over geological time. The equatorial regions, protected by the closed field lines, show brighter and less radiation-processed surfaces. The aurora marks not just a light show, but a fundamental physical boundary, the line between the protected interior and the exposed exterior of Ganymede's magnetic domain. You drift back down toward the magnetopause. The boundary between Ganymede's field and Jupiter's is not a quiet place. Magnetic reconnection events are happening intermittently along this boundary, moments when anti-parallel field lines from the two magnetospheres meet and undergo topological rearrangement, releasing energy and accelerating particles. These reconnection events are the same fundamental process that drives solar flares, that drives the energetic events in Earth's magnetosphere during geomagnetic storms. The Galileo spacecraft, during its close flybys of Ganymede between 1996 and 2000, passed through this magnetopause boundary multiple times. Its instruments recorded the changes in field strength and particle populations as it crossed back and forth between Jupiter's domain and Ganymede's. Each crossing told scientists something more about the structure and dynamics of Ganymede's magnetic environment. The data from those flybys established definitively that Ganymede's magnetic field is an intrinsic field generated internally, not induced by external sources, and that it has a dipole character with a north and south pole tilted roughly 176 degrees from the rotation axis. The tilt means that Ganymede's magnetic poles are close to its geographic equator, not close to its geographic poles. If you were standing at Ganymede's geographic North Pole, the magnetic field at your location would be nearly horizontal, pointing roughly southward toward the equator. This is very different from Earth, where the magnetic poles are reasonably close to the geographic poles, and the field lines at high latitudes are nearly vertical. On Ganymede, the geometry of the field is rotated dramatically with respect to the spin axis, and this affects everything about how the magnetosphere interacts with Jupiter's field and where the auroras form. You cross back through the magnetovas and descend toward the surface. Ganymede's surface comes up below you, the grooved terrain lit in thin cold sunlight and the warmer reflected glow of Jupiter. You are coming down toward the South Polar region. Below you, deep in the ice, deep below the rock, deep in the liquid iron core, the geodynamo turns. It generates the field. The field creates the magnetosphere. The magnetosphere shapes the auroras, and the auroras revealed the ocean. You come to rest on the surface again, near the South Polar region, where the ancient dark terrain extends in all directions, heavily cratered, unchanged. The silence here is the silence of a place that has never heard a sound. Complete. Unbroken. The magnetic field presses through the ground beneath your feet. You cannot feel it, but it passes through you, through the ice, through the rock, through the silicate mantle, and down into the iron core where the convection cells circulate, where the geodynamo turns, where the field is born and sustained. And above the field, above the magnetopause, Jupiter's vast magnetosphere presses in, held at arm's length by the small but persistent internal field of the largest moon in the solar system. Beneath 150 kilometers of ice, hundreds of billions of tons of ancient salt water sit in darkness, pressing against the rock below and the ice above, warmed by the residual heat of Ganymede's still active interior, conducting electricity slowly through their dissolved salts, responding to Jupiter's changing magnetic field, leaving their signature in ultraviolet light, visible to a telescope in orbit around Earth. The ocean has been there for billions of years. No spacecraft has ever been designed to reach it. No instrument has sampled it. But its existence is understood. Its size is estimated. Its composition is partially inferred. And in the decade ahead, a spacecraft already traveling through the inner solar system is going to change what we know. For now, you are back on the surface. The grooves stretch out in front of you. Jupiter holds its place in the sky. The aurora glows invisibly above the poles. The magnetic field lines curve through space around you, invisible architecture, ancient and ongoing. The cold is even and total. And 150 kilometers below your feet, the ocean waits. 150 kilometers is not a large number by the standards of this solar system. It is smaller than the distance between many cities on Earth. It is a distance a commercial aircraft could cover in less than 20 minutes. But beneath Ganymede's surface, those 150 kilometers are not air and cloud and open sky. They are ice. Compressed, ancient layered ice, water that fell into this moon's outer shell during the earliest epochs of the solar system and has been frozen in place ever since, pressed under its own weight, slowly restructured by pressure into crystalline forms that no longer resemble the ice in any glass of water on Earth. The topmost layer, the surface you were just standing on, is a mixture of silicate dust, impact ejecta, and water ice, irradiated for billions of years by Jupiter's magnetospheric particles until it has taken on a brownish-gray tinge in the older dark regions. Below that, the ice becomes purer, denser. The pressure at increasing depth changes the crystal structure of the water ice in a process well understood by high-pressure physics. At the surface, water ice exists in the form called ice-eye, the familiar hexagonal crystal structure of ordinary ice, the form that floats on liquid water, the form that makes snowflakes. As you descend through Ganymede's ice shell, the pressure increases steadily and the ice transitions through higher density phases. At depths of tens of kilometers, the crystal lattice reorganizes into Ice 3, then Ice Vive, then Ice 6, each phase denser than the last, each requiring more energy to form, each fundamentally different in structure from the ice at the surface. These high-pressure ice phases do not float on liquid water. They sink. This matters because it affects the dynamics of Ganymede's interior, the way heat moves through the ice shell, the way material can or cannot convect, the way the ocean and the rocky mantle below are separated and insulated from each other. You are descending now. Not physically, not in any sense that a spacecraft or a drill could replicate, but in understanding, in the slow, deliberate accumulation of what science has measured and inferred and calculated about what lies below. At a depth of approximately 150 kilometers, the pressure and residual internal heat reach a threshold. The ice is no longer ice. It is water. Liquid water. Salty, cold by surface standards, dark by any standard, but liquid. The ocean begins here, at the base of the ice shell, and it does not end quickly. The estimated thickness of Ganymede's subsurface ocean ranges, in different models, from 500 to 900 kilometers. The most commonly cited estimate is approximately 800 kilometers deep. For comparison, the average depth of Earth's oceans is approximately 3.7 kilometers. The deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, is approximately 11 kilometers below the surface. Ganymede's subsurface ocean is estimated to be 800 kilometers deep. It is not a shallow film of water trapped beneath ice. It is an ocean by every meaningful definition of the word, and it is larger than any ocean that has ever existed on Earth. The total volume of water in Ganymede's subsurface ocean is estimated to be approximately 25 to 35 times the total volume of all of Earth's oceans combined. Earth holds approximately 1.335 billion cubic kilometers of ocean water. Ganymede may hold between 33 and 47 billion cubic kilometers. All of it in darkness. All of it under pressure. All of it separated from the nearest sunlight by 150 kilometers of high-pressure ice. You have reached the top of the ocean. The boundary between the base of the ice shell and the top of the liquid water is not a sharp line in the way a lake's surface is sharp. It is a transition zone, a region where ice and water coexist, where the temperature hovers near the freezing point, modified by pressure, where small changes in the local heat flux or salt concentration can push material from one phase to the other. The water here at the very top of the ocean is the coldest water in the ocean. It is in contact with the ice above it, which is itself being cooled from above by the minus 113 degrees Celsius surface temperature. Heat flows from warmer to cooler, always, and the ocean's top is losing heat slowly upward through the ice shell. The water just below the ice boundary is only a few degrees above the pressure-adjusted freezing point. But it is liquid. And below you, extending downward for 800 kilometers, the temperature slowly increases. The heat source driving that temperature gradient is at the bottom, at the interface between the ocean and the rocky silicate mantle beneath it. There, the rock is warmer than the water. The warmth comes from two sources operating simultaneously. The first is tidal heating. The Laplace resonance maintains a slight eccentricity in Ganymede's orbit, and as Ganymede moves closer to and farther from Jupiter in each orbital cycle, Jupiter's tidal force compresses and releases the interior in a slow rhythmic flexing that deposits energy as heat. The second heat source is radiogenic, the decay of long-lived radioactive isotopes distributed through the silicate rock of the mantle and core. Uranium-238, thorium-232, and potassium-40 all decay with half-lives measured in billions of years, releasing energy continuously in the form of heat. These isotopes have been decaying since Ganymede formed 4.5 billion years ago. Their heat output has diminished as the radioactive inventory is slowly depleted, but they are still producing heat today, and that heat flows upward from the rock into the ocean. The combination of tidal heating and radiogenic heating keeps the base of the ocean warm enough to remain liquid. Without these heat sources, Ganymede's ocean would have frozen solid billions of years ago. With them, it has persisted, a vast, dark, pressurized ocean maintained by the gravitational dance of 3 moons around a gas giant, and by the slow decay of atoms left over from the formation of the solar system. You descend into the ocean. The water here is not transparent. It is not the clear blue of a tropical sea. There is no light. There has never been light. Not once in 4.5 billion years has a single photon from the sun reached the water you are moving through now. The darkness is not the darkness of a room with the lights off, where your eyes slowly adjust and shadows resolve into shapes. This is absolute darkness, the darkness of a place where light has never been and cannot be. The pressure increases steadily as you descend. At the top of the ocean, the pressure is already enormous, hundreds of atmospheres, the weight of 150 kilometers of ice, pressing down from above. Ganymede's surface gravity is approximately 1.43 meters per second squared, about 14.6% of Earth's surface gravity. The lower gravity means the pressure increase with depth is gentler than on Earth. But the ocean is 800 kilometers deep, and at the bottom the pressure is extraordinary, thousands of atmospheres, far exceeding the pressure at the bottom of Earth's deepest ocean trenches. At those pressures, at the very base of the ocean where it meets the rocky mantle, the water itself may not be entirely liquid in the ordinary sense. Some models suggest that the very deepest part of Ganymede's ocean may contain high-pressure ice phases, Ice 6 or even Ice 7, forming a thin layer between the bulk liquid ocean and the rocky seafloor. Ice 7 is a form of water that remains solid at room temperature if the pressure is high enough, approximately 30,000 atmospheres. It is water, but it would cut glass. The boundaries between ice and water and rock in Ganymede's deep interior are not clean layers separated by sharp lines. They are zones of transition, governed by pressure and temperature and composition, all of which vary continuously with depth. The silicate rock of the mantle begins below the ocean floor, or below whatever ice-water rock transition zone exists at the deepest point. And that rock is not cold, geologically inert stone. It is warm. It is releasing heat. In some regions of the ocean floor, where the mantle is warmer, or where tidal heating is concentrated by local geology, there may be hydrothermal activity, warm water rising from fractures in the seafloor rock, carrying dissolved minerals upward into the ocean. There is no direct evidence of hydrothermal vents on Ganymede's ocean floor. But the conditions required for hydrothermal activity, liquid water in contact with warm silicate rock with a heat gradient driving circulation, appear to be present based on the best current models of Ganymede's interior. On Earth, hydrothermal vents at the seafloor support entire ecosystems, communities of bacteria, tube worms, crabs, shrimp, and fish that derive their energy not from sunlight, but from the chemical energy in hydrogen sulfide and other reduced compounds venting from the seafloor. These ecosystems were discovered in 1977 at the Galapagos Rift, and their existence demonstrated for the first time that life on Earth is not universally dependent on sunlight. Life can run on chemistry. Life can run on heat. Life can run in complete darkness, under crushing pressure. This discovery fundamentally changed the conversation about where life might exist in the solar system. Because if life does not require sunlight, if the only requirements are liquid water, a source of chemical energy, and the relevant organic chemistry, then the subsurface ocean of Ganymede becomes a place that cannot be ruled out. Not confirmed. Not even likely based on current evidence. But not ruled out. The salinity of the ocean is a subject of active scientific investigation. The 2015 Hubble Aurora study established that the ocean must be electrically conductive. Electrical conductivity in a water body is produced by dissolved ions, which means dissolved salts. The dissolved salts could be magnesium sulfate, a compound that forms readily when water reacts with silicate rock rich in magnesium minerals. They could include sodium chloride, the common salt of Earth's oceans. They could include a mixture of many ionic species produced by 4.5 billion years of water-rock interaction at the seafloor. Water is not a passive solvent. It attacks rock. At the temperatures and pressures of Ganymede's seafloor, water reacts with iron and magnesium-rich silicate minerals in a process called serpentinization, producing serpentine minerals, magnetite, and crucially, hydrogen gas. The hydrogen gas produced by serpentinization is a chemical fuel. On Earth, some microorganisms in deep sea environments consume hydrogen produced by serpentinization as their primary energy source, combining it with carbon dioxide to produce methane and water in a reaction that releases energy. These organisms are called methanogens. They do not require sunlight. They do not require oxygen. They live in complete darkness, sustained entirely by the chemical gradient between hydrogen and carbon dioxide. If serpentinization is occurring on Ganymede's seafloor, and the physics suggests it is plausible, though not confirmed, then the chemical raw materials for this most basic form of chemolithotrophy are present. The ocean of Ganymede, in the deepest scientific sense of the word, is not sterile by necessity. It may be sterile. The probability of life in Ganymede's ocean is considered by most astrobiologists to be low, lower than Europa's, because the ice shell is thicker and the exchange of oxidants from the surface to the ocean is believed to be less efficient. But the concept of impossibility does not apply, and that distinction matters enormously. The question of life in the solar system is not a binary question. It is not simply life or no life. It is a question about thresholds, about what conditions are sufficient, what conditions are necessary, and where the boundaries between chemistry and biology actually lie. On Earth, the transition from chemistry to biology happened at least once, approximately 3.5 to 4 billion years ago, in conditions that were different from today's surface in ways that are still being actively debated. The early Earth had no oxygen in its atmosphere. It had a different mix of dissolved chemicals in its oceans. It had more intense ultraviolet radiation reaching the surface, more volcanic activity, a stronger geothermal heat flux, and a much younger, more active geological environment. Life emerged in those conditions? Which conditions were strictly necessary and which were merely present at the time is not fully known. This matters for Ganymede because the question is not whether Ganymede's ocean resembles Earth's modern ocean. It does not. It is far colder near the top, far more pressurized, far darker, likely more saline in some chemical sense, and separated from any possibility of surface chemistry by 150 kilometers of ice. The question is whether Ganymede's ocean resembles Earth's ocean at the time and place where life first appeared, in the warm, dark, chemically rich environment of a hydrothermal system at the bottom of an early ocean, far from sunlight, sustained by the chemical energy of water reacting with rock. That environment, if it exists at Ganymede's seafloor, has been running continuously for 4.5 billion years. On Earth, the time between the formation of the ocean and the appearance of the earliest evidence of life was perhaps 500 million years. Ganymede has had 9 times that long. If the conditions at the seafloor are remotely similar to what was required for life on Earth, 4.5 billion years is more than sufficient time. This is not an argument that life exists in Ganymede's ocean. It is an argument for why the question deserves to be asked precisely, investigated rigorously, and answered by measurement rather than assumption. The ocean does not care about the question. It continues, pressurized and dark, reacting water with rock at the seafloor, inducing electrical currents that fingerprint the aurora hundreds of kilometers above, keeping its ancient chemistry in whatever state it has reached after 4.5 billion years of working in the dark. You remain still in the water. The pressure holds you. The darkness is absolute. If there is anything else here, any organism, any biological chemistry, any lipid membrane or self-replicating molecule, it would be invisible to you in this darkness and at this scale. Life, if it exists here, is microbial. Individual cells or mats of cells clinging to the warm rock of the seafloor, or suspended in the water column near a hydrothermal vent, or living at the very boundary between the ocean and the ice above, where the chemistry is different, where the temperature gradient is steepest. Life, if it exists here, does not know it is here. It does not experience the darkness or the pressure or the isolation. It simply metabolizes. It simply replicates. It simply continues, as life does, as long as the energy holds out. And the energy here shows no sign of running out. The tidal flexing continues. The radioactive isotopes continue to decay. The rock continues to react with the water. The gradients that sustain chemistry and possibly biology show no signs of ceasing within any time frame that matters to a living organism, or to the scientists who want to know whether any living organism is there. You move through the dark water slowly. The pressure around you is immense. The temperature is cold near the top and warmer near the bottom, a slow gradient over 800 kilometers. The ocean is not still. It cannot be perfectly still if there is a temperature gradient. Heat drives convection, and convection drives circulation. But the circulation is slow, unhurried, geological. In the darkness at the mid-depth of the ocean, you pause. Above you, 150 kilometers of layered ice, and then the surface, and then the silence of space, and then Jupiter hanging in the sky. Below you, 400 more kilometers of dark ocean, and then the seafloor, and then the warm silicate rock, and then the deep mantle, and then the partially liquid iron core where the geodynamo turns and generates the magnetic field that wraps the surface above in invisible protection. This is what a differentiated body looks like from the inside. Ice, ocean, rock, iron. 4 concentric shells, each one with its own temperature and pressure and chemistry, each one separated from the next by a transition zone that is itself a zone of ongoing physics. This is what happens when a world forms from the chaos of the early solar system. With enough mass, enough heat, enough time, the materials separate by density, the heaviest sinking to the center, the lightest rising to the surface, the middle layers organizing themselves into a structure as orderly, in its own way, as the layers of an onion. You begin ascending, the pressure decreasing steadily, the temperature dropping slightly as you approach the base of the ice shell. You cross it from liquid to solid, from the water that has been sitting here for billions of years into the ice that has been sitting on top of it for billions of years. The two in contact, exchanging heat slowly, a boundary and dynamic equilibrium that has been maintained for an unimaginable length of time. You rise through the ice, through Ice 6, under thousands of atmospheres, through Ice Phi, through Ice 3, the pressure falling as you ascend, the crystal structure of the ice reorganizing at each phase boundary into a less dense, less compressed form, through the mixed zone of silicate dust and ice near the surface. And then you emerge. You are on the surface again. The grooves are still there. Jupiter is still there. The cold is still there. But you carry with you now an understanding of what is underneath, of the 150 kilometers of layered ice, the 800 kilometers of dark ocean, the silicate mantle, the iron core, a structure that has been in place for 4.5 billion years and shows no sign of ending. The surface beneath your feet is not just a surface. It is the ceiling of one of the largest oceans in the solar system. And the ocean below does not know you were there. It will not know for billions of years more. It has its own time, its own chemistry, its own dark, unhurried existence. And somewhere in that darkness, somewhere in the 800 kilometers of pressurized water between the ice ceiling and the rock floor, the answer to one of the oldest questions in science may already exist, or may never have formed. The ocean does not tell you which. It does not speak. It only continues. You stand on the surface of Ganymede and look up at Jupiter and understand, with a clarity that comes only from scale, that you are standing on something that was already old when the first multicellular organisms appeared on Earth. Something that was already old when the dinosaurs went extinct. Something that will still be here when the sun begins to expand and the inner planets are consumed and the outer solar system grows briefly warmer before the long cold sets in. Ganymede will still be here. The ocean may still be liquid. The magnetic field may still be turning. And the grooves you are standing in, carved by geological forces that ended 2 billion years ago, will still be exactly where they are now. This world does not hurry. The Laplace resonance keeps its time, and the iron core keeps its heat, and the ocean keeps its dark, unhurried existence, and you stand at the boundary between the known and the unreachable, and simply take in the scale of what is here. You sit down again on the ridge of a groove system. The ice is cold. Jupiter is vast. The silence is the kind that has never been broken by any sound, because sound requires a medium to travel through, and the surface of Ganymede has no atmosphere thick enough to carry it. Your heartbeat is the loudest thing in this place, and even that is only in your own chest. In, out. In this silence, in this scale, the question of how Ganymede came to be here, of how this particular arrangement of ice and rock and iron and water came to exist, orbiting this particular gas giant at this particular distance from the sun, becomes unavoidable. The answer requires going backward. A long way backward? 4.5 billion years backward, to a time when there was no Ganymede, no Jupiter system, no solar system as we know it, only a vast rotating disk of gas and dust, slowly condensing under its own gravity, with the sun at its center not yet fully ignited, and the planets still being assembled from the raw material of stellar formation. That is where this world came from. And that is where this journey goes next. You close your eyes on the surface of Ganymede, the grooves still beneath you, the ocean still below, Jupiter still above, and you let the timeline reverse. 4.5 billion years. Going back. The solar system was not born all at once. It condensed. Approximately 4.6 billion years ago, a cloud of gas and dust in one arm of the Milky Way, a molecular cloud containing hydrogen, helium, and the heavier elements synthesized in previous generations of stars, began to collapse. The trigger for that collapse is not precisely known. One leading hypothesis is that a nearby supernova, the explosive death of a massive star, sent a shockwave through the molecular cloud, compressing it past the threshold at which its own gravity could take over. Another hypothesis is that the collapse was triggered by a gravitational instability in the galactic disk, with no single triggering event required. What is known is the result. The cloud collapsed. As it collapsed, it began to rotate faster, just as an ice skater spins faster when drawing their arms inward. The conservation of angular momentum caused the collapsing cloud to spin up. The spinning caused the cloud to flatten into a disk. At the center of the disk, material piled up, pressure and temperature increased, and eventually, after perhaps 100,000 years of accumulation, nuclear fusion ignited. The sun was born. But the disk around the sun did not disappear. It persisted, a protoplanetary disk of gas and dust, extending outward from the young sun for hundreds of astronomical units. In this disk, solid particles collided and stuck together. Dust grains became pebbles. Pebbles became boulders. Boulders became planetesimals, objects tens to hundreds of kilometers across, large enough to have gravity of their own, large enough to begin attracting smaller objects through gravitational attraction rather than simply sticking on contact. Planetesimals became protoplanets. The largest protoplanets swept up material from their orbital zones and became planets. Jupiter formed early. This is important. Jupiter formed faster than any other planet in the solar system, accumulating its massive rock and ice core within the first few million years of the solar system's existence, and then rapidly accreting the gas of the protoplanetary disk before the young sun's radiation could disperse it. The core accretion model of Jupiter's formation suggests that Jupiter began as a solid core of rock and ice approximately 10 to 20 Earth masses, formed in the cold outer solar system where volatile compounds could freeze and contribute to the solid material available for accretion. Once that core reached a critical mass, it began to accrete gas directly from the surrounding disk, and the accretion rate increased rapidly in a runaway process. Jupiter went from roughly 20 Earth masses to its current mass of 318 Earth masses in a period estimated to be shorter than 1,000,000 years, an eye blink by solar system standards. This rapid growth gave Jupiter an outsized influence on the subsequent evolution of the solar system. One major consequence was the Grand Tack hypothesis, a model of the early solar system's evolution proposed by Walsh, Morbidelli, and colleagues in 2011, which suggests that Jupiter, after forming at approximately 3.5 astronomical units from the Sun, migrated inward through the protoplanetary disk to approximately 1.5 astronomical units before being halted and reversed by the formation of Saturn, after which both gas giants migrated outward together to their current positions. This inward and then outward migration of Jupiter, the tack like a sailing ship changing direction, would have dramatically altered the distribution of solid material in the solar system, depleting the asteroid belt, sending material inward toward the terrestrial planets, and reshaping the conditions in the outer solar system. The Grand Tack is not universally accepted. It is a hypothesis, not an established fact, and alternative models of early solar system evolution exist. But the general principle that the early solar system was more dynamically violent than its current orderly appearance suggests, with planets migrating significantly from their formation positions, is supported by multiple lines of evidence. In the region of the disk around Jupiter, a disk of material orbiting the gas giant itself, called the Jovian subdisk or circumjovian disk, the same process that built the planets from the solar disk was building the Galilean moons. solid particles in the Jovian subdisk accumulated. Planetesimals formed. Protoplanetary bodies accreted. And from this process, 4 large moons emerged: Io, Europa, Ganymede, and Callisto. Ganymede formed at a position in the Jovian subdisk where the temperature was cold enough for water ice to be a major constituent of the solid material available for accretion. The frost line, the distance from Jupiter beyond which water ice could exist as a solid in the disk, ran through the region where Ganymede formed. This is why Ganymede is roughly half ice by mass. Not because ice was added to a pre-existing rock body, but because the building blocks of Ganymede, the planetesimals that aggregated over millions of years to form this moon, were themselves composed of roughly equal mixtures of silicate rock and water ice. The accretion process was not gentle. The early Jovian subdisk was a violent environment, planetesimals traveling at high velocities relative to one another, collisions releasing enormous amounts of energy, each major impact generating enough heat to melt or partially melt the accreting body. As Ganymede grew, the energy of incoming impacts was deposited in its interior, heating it from the inside out. The interior melted. And when the interior melted, the materials that had been mixed together, iron, rock, ice, water, were free to separate by density. The iron heaviest sank toward the center. The silicate rock, less dense than iron but denser than water, settled into a mantle around the iron core. The water and ice, lightest of all, floated to the surface. This process, differentiation, released additional energy of its own. As iron sank through the rocky material, the gravitational potential energy of the rearrangement was converted to heat, further warming the interior, further driving differentiation. The process was self-reinforcing. Once started, it ran to completion. By the time Ganymede had accreted to approximately its current size, a process that may have taken between 1 and 10 million years, it was already differentiated, already had a core, already had a mantle, already had an outer layer of ice and water, and already, perhaps, had the beginning of a liquid iron core that would eventually sustain the magnetic field you pass through on your way to the surface. The accretion phase ended. The Jovian subdisk was depleted. The remaining planetesimals that had not been incorporated into the Galilean moons were gradually ejected by gravitational interactions with Jupiter or with the moons themselves. The solar system was not yet finished being violent. The period known as the Late Heavy Bombardment, approximately 3.8 to 4.1 billion years ago, sent a storm of impactors across the inner solar system and into the outer solar system as well, and Ganymede's ancient dark terrain bears the scars of that bombardment in its crater-saturated surface. The primary structure of the Jovian system was in place. Jupiter dominated. 4 large moons orbited it. Then, perhaps 3 billion years ago, something happened inside Ganymede. The interior was still warm from formation, still being heated by radioactive decay and tidal flexing, and that warmth drove geological activity at the surface. The outer crust, brittle, cold, heavily cratered, began to stretch. Faults opened. Rifts formed along zones of weakness. And from those rifts, fresh material welled up from below, lighter, brighter ice and rock that had not been exposed to billions of years of space weathering. The grooved terrain formed. The sulci carved themselves across 2/3 of Ganymede's surface in a period of geological activity that lasted perhaps 1 billion years. Then it stopped. The interior cooled slightly. The crust thickened. The geological activity ended. And for the past 1.5 to 2 billion years, the surface has been exactly as it is now. Grooves and dark terrain, and craters slowly accumulating, space weathering slowly darkening the bright sulci, the occasional impact adding a new crater to the count, but no new rifts, no new grooves, no new geological reshaping. The surface is finished. The interior is not. Deep inside, the ocean persists. The geodynamo turns. The tidal flexing continues. And the Laplace resonance, the gravitational metronome that has kept Io, Europa, and Ganymede in their 1:4 orbital ratio since the early solar system, continues to tick. It has ticked 4.5 billion times for every year of Ganymede's existence. Each tick is one complete orbit of Io. Each 4 ticks is one complete orbit of Ganymede. The mathematics has not slipped. Not once. Not by a fraction of a second. The gravitational geometry of the Jovian system is that precise, and it has been that precise since before the Earth had continents. You stand on the grooved terrain and understand it differently now. The ridges and furrows beneath your feet are not just surface features. They are evidence of an interior that was once active. They are the healed over scars of a world that cracked open along its fault lines and then slowly closed again, leaving these parallel grooves as the permanent record. They are geological writing. Each of the 4 Galilean moons tells a different story about what happens when a moon forms in the shadow of a gas giant. Io, closest to Jupiter, receiving the most intense tidal heating, so intense that the heat cannot escape through the crust fast enough and must erupt through hundreds of active volcanoes spread across the surface. Io resurfaces itself continuously. The volcanic deposits accumulate so rapidly that Io's surface changes measurably over years, not geological epochs. There is no crater record on Io because no crater survives long enough to be preserved. Each impact scar is buried under fresh volcanic material within centuries or millennia. Europa, slightly farther from Jupiter, receiving less tidal heating, but still enough to maintain a subsurface ocean beneath an ice shell estimated at 10 to 30 kilometers thick. Europa's ocean is believed to be in direct contact with a rocky seafloor without the high-pressure ice layers that separate Ganymede's ocean from its rock. This direct water-rock contact, combined with the radiation-driven production of oxidants at Europa's surface and their potential delivery to the ocean through the ice, makes Europa the moon most commonly cited in discussions of extraterrestrial habitability. Ganymede, largest, most massive, differentiated fully with a magnetic field no other moon possesses, an ocean estimated at 800 kilometers deep, containing more water than all of Earth's oceans combined, and a thick ice shell that insulates the ocean from the surface radiation environment. Callisto, the outermost of the 4 large moons, at a distance of approximately 1.88 million kilometers from Jupiter, receiving almost no tidal heating. Callisto may have a subsurface ocean. There is some evidence from Galileo spacecraft magnetometer data of an induced magnetic field that could indicate a conductive layer, but it is not confirmed. Callisto's surface is the oldest in the Jovian system, covered in ancient craters with no evidence of internal geological activity. Callisto may never have fully differentiated. Its interior may still be a roughly homogeneous mixture of rock and ice, incompletely separated, a world that simply did not receive enough heat to reorganize itself the way Ganymede did. The contrast between Ganymede and Callisto is striking precisely because they formed from similar material in the same disk. Ganymede differentiated completely. Callisto did not. The difference is believed to come down to the rate of accretion, how quickly each moon grew. If a moon accretes rapidly, the impact energy from infalling material is deposited faster than it can radiate away, heating the interior efficiently and driving differentiation. If a moon accretes slowly, the heat is lost to space between impacts, and the interior never reaches the temperatures required for full differentiation. Ganymede, being larger and perhaps forming in a more material-rich zone of the disk, accreted more rapidly. Callisto accreted more slowly. The result, 4.5 billion years later, is a magnetic field on one and none on the other, a vast, deep ocean on one, and an uncertain, unconfirmed conductive layer on the other, a geologically complex layered world, and a geologically simple ancient surface. 4 worlds. 4 answers to the same question. All of them orbiting the same gas giant. All of them formed from the same disk of material. All of them shaped by the same fundamental forces, applied at slightly different distances and intensities. For now, you stand on the grooved surface, with Jupiter filling the sky and the ancient dark terrain stretching to your left, and the grooves running off to your right, and the ocean 150 kilometers below your feet, and the iron core 2,600 kilometers further below that. 4.5 billion years behind you. An unknown but vast amount of time ahead. The Laplace resonance keeping time. The ocean waiting. The surface unchanging. You are standing at the intersection of deep time and the present moment, on a world that was already ancient before any human existed to wonder about it. And it will be exactly this way long after. The cold is constant. Jupiter turns slowly above you, enormous and unhurried. The ocean, 150 kilometers below, continues its existence, indifferent to questions, indifferent to instruments, indifferent to the small warm beings on a small warm planet more than 600 million kilometers away, who have, through the elegant indirection of aurora measurements and magnetic field analysis, managed to understand that it is there. It is there. It has always been there. And soon a spacecraft will arrive to learn more about it than has ever been known. But before that arrival, it is worth pausing on a longer question. Not the question of what JUICE will find. The question of what Ganymede will be doing in 1 billion years. In 5 billion years. In the deep future when the sun has changed. The sun is currently in the middle of its main sequence phase, the long, stable period of hydrogen fusion in its core that has been ongoing for approximately 4.6 billion years and will continue for approximately another 5 billion years. During this period, the sun's luminosity is slowly increasing by approximately 10% every billion years. This gradual brightening has consequences throughout the solar system. In the inner solar system, it means the habitable zone, the region where liquid water can exist on a planetary surface, is slowly migrating outward. In the outer solar system, it means the surfaces of icy moons are very slowly warming, very slowly changing, the sublimation rates of surface ices slowly increasing. On Ganymede, the current surface temperature of minus 113 degrees Celsius on the sunlit side will gradually increase over the next few billion years as the sun brightens. The effect is small on any human timescale, but over billions of years, it is real. In approximately 5 billion years, the sun will exhaust the hydrogen in its core. Nuclear fusion will continue in a shell around the core, and the outer layers of the sun will expand enormously. The sun will become a red giant, swelling to a radius estimated at approximately 1.2 astronomical units, engulfing Mercury, Venus, and likely Earth. During the red giant phase, the sun's luminosity will increase by a factor of approximately 1,000 to 2,000. At Jupiter's distance, the energy flux from the red giant sun will be vastly higher than it is today. The surfaces of the icy Galilean moons will warm dramatically. Ganymede's surface ice will begin to sublime and eventually melt. The thin exosphere will thicken, not to a full atmosphere comparable to Earth's, because Ganymede's gravity is insufficient to retain a dense atmosphere against the intense solar wind of the red giant phase. But for a period, perhaps tens of millions of years, the surface conditions on Ganymede may be more temperate than they have been at any point in the moon's history. The subsurface ocean, if it still exists, will be heated from above as well as from below. The ice shell will thin. Whether it will thin enough for the ocean to reach the surface, whether Ganymede will ever have a surface ocean, is uncertain, dependent on models that are not yet precise enough to answer with confidence. But the possibility exists. A world that has held its ocean sealed beneath 150 kilometers of ice for 4.5 billion years may, in the far future, open that ocean to the sky. For a cosmically brief period, before the sun's red giant phase ends, before the outer layers are shed as a planetary nebula and the core contracts to a white dwarf, the conditions in the outer solar system will be briefly dramatically different from anything they have been. And then the sun will become a white dwarf, a dense remnant the size of Earth, emitting a fraction of its current luminosity. The outer solar system will cool again. Jupiter will still be there. Gas giants survive the red giant phase of their host stars relatively intact, losing some mass from their upper atmospheres, but retaining their bulk. Ganymede will still be orbiting it. The Laplace resonance will still be ticking. The magnetic field may still be turning, though the iron core will have cooled further in those additional 5 billion years. The ocean, if it survived the red giant warming phase and refroze as the white dwarf cooled, will be beneath its ice again. Sealed, dark, patient. The grooves carved 2 billion years ago will still be exactly where they are. This world is not in a hurry. It never has been. On April 14th, 2023, a rocket lifted off from the Guyana Space Center on the northeastern coast of South America. It carried a spacecraft weighing approximately 6,000 kilograms at launch, the heaviest interplanetary science mission the European Space Agency had ever built. Its name was JUICE, Jupiter Icy Moons Explorer. At the moment of launch, it was sitting on top of an Ariane 5 rocket, surrounded by the heat and noise of combustion, moving from stillness into motion in a matter of seconds. It cleared the launch tower. It cleared the atmosphere. It separated from the rocket upper stage. And it began the longest, most complex journey any spacecraft of its kind had ever undertaken to the outer solar system. You are still on Ganymede's surface. Jupiter is still above you. The ocean is still 150 kilometers below. But somewhere between here and the inner solar system, traveling at tens of kilometers per second, JUICE is on its way. It will not arrive quickly. The route to Jupiter is not a straight line. It never is for a spacecraft launched from Earth. The laws of orbital mechanics, the same laws that govern the Laplace resonance beneath your feet, require that spacecraft use gravity assists to reach the outer planets efficiently. JUICE's trajectory includes a lunar Earth gravity assist in August 2024, a Venus flyby in August 2025, 2 more Earth flybys in 2026 and 2029, and a Jupiter arrival in July 2031. 8 years of travel. 8 years of crossing the space between Earth and Jupiter, a distance that varies between approximately 590 million and 960 million kilometers, depending on where the 2 planets are in their respective orbits. 8 years during which the spacecraft will be checked, tested, calibrated, its instruments powered on and off, its trajectory corrected by small thruster firings, its communication link with Earth maintained across a distance that will eventually require signals traveling at the speed of light more than 40 minutes to cross. JUICE carries 10 scientific instruments. A radar sounder called RIME, Radar for Icy Moon Exploration, designed to penetrate up to 9 kilometers into the icy surfaces of Ganymede, Europa, and Callisto, using radio waves to probe the subsurface structure. 9 kilometers is not 150 kilometers. RIME will not reach Ganymede's ocean directly, but it will reveal the structure of the upper ice shell in unprecedented detail, the layering, the fractures, the inclusions, the density variations, and those measurements will constrain models of the full ice shell thickness and the conditions at the ice-ocean boundary in ways that no previous instrument has been able to do. A magnetometer called JMAG, designed to measure Ganymede's magnetic field, with precision far exceeding the Galileo spacecraft's measurements from the 1990s. JMAG will map the field's structure across the entire surface, measuring its strength and direction at many altitudes and latitudes, looking for the induced component, the part of the magnetic field generated not by the core, but by electrical currents flowing in the subsurface ocean in response to Jupiter's varying field. The amplitude and phase of that induced field, measured precisely, will constrain the depth, thickness, and conductivity of the ocean. It will not see the ocean directly, but it will measure the ocean's electromagnetic shadow with a precision that will narrow the range of uncertainty in ocean models to a degree that current data cannot achieve. An ultraviolet spectrograph called UVS, building on the Hubble observations that first established the subsurface ocean's existence, but from an orbit around Ganymede, rather than from a telescope at Earth, and with far better angular resolution. UVS will observe the aurora continuously, mapping the rocking of the auroral bands over many orbital periods, building a dataset of Ganymede's magnetospheric dynamics that will take years to fully analyze. A visible and near-infrared imaging system called MAGIS, mapping the surface composition across all wavelengths in that range, looking for the spectral signatures of specific minerals, salts, and organic compounds on the surface. If magnesium sulfate or other salts from the ocean have been cycled upward through the ice and exposed at the surface, MAGIS will detect their spectral signatures. The surface chemistry of Ganymede, mapped at high resolution, is a record of the ocean chemistry below. Reading that record is one of JUICE's primary scientific objectives. A gravity and radio science experiment called 3GM, using the extremely precise measurement of the spacecraft's velocity via the Doppler shift of its radio signals to infer the gravitational field of Ganymede with extraordinary precision. The internal mass distribution of Ganymede, how mass is arranged between the core, mantle, ocean, and ice shell, determines the gravitational field's detailed structure. Measuring that structure constrains the internal model. The ocean's depth and density, inferred from the gravitational field combined with the magnetic measurements, will be known after JUICE far better than they are known today. All of these instruments working together over multiple years of orbital operations at Ganymede will build a picture of this moon's interior with a resolution and completeness that is simply not possible from Earth or from a brief flyby. JUICE will not just visit Ganymede. It will live there. After its arrival at Jupiter in July 2031, JUICE will spend approximately 2.5 years in the Jovian system, performing flybys of Ganymede, Europa, and Callisto, collecting data on all 3 moons and on the Jovian magnetospheric environment. Then, in late 2034, JUICE will perform a series of maneuvers to enter orbit around Ganymede, the first spacecraft ever to orbit a moon other than Earth's moon. It will spend approximately 9 months in Ganymede orbit, circling the moon at different altitudes and inclinations, building the most complete scientific dataset ever assembled about any body in the outer solar system. In 2035, when the mission's fuel is exhausted and its scientific objectives are complete, JUICE will be commanded to impact Ganymede's surface. A controlled impact. A final data collection opportunity as the spacecraft descends through the thin exosphere at close range, instruments still running. And then the spacecraft that launched from South America in 2023, that spent 8 years crossing the solar system, that spent years in orbit around this moon, will become part of that moon's surface. A small piece of human engineering buried in the ice. The idea of it is something to sit with. The chain of effort goes back further than JUICE. It goes back to the mathematical work of Pierre-Simon Laplace, who in the 1780s proved that the 1-2-4 orbital resonance of Io, Europa, and Ganymede was stable, that the gravitational interactions of the 3 moons would maintain that resonance indefinitely rather than disrupting it. The resonance he described had been running for 4.5 billion years before he proved it was stable, and it has continued running for the 2.5 centuries since. It goes back to the Voyager missions. Voyager 1 launched in September 1977 and flew past Jupiter in March 1979. On March 5, 1979, Voyager 1 made its closest approach to Jupiter, passing within 349,000 kilometers of the planet's cloud tops. During the Jupiter encounter, Voyager 1 captured the first close-up images of the Galilean moons. The images of Ganymede showed, for the first time, the two-terrene nature of the surface, the ancient dark terrain and the younger grooved terrain, with enough resolution to begin understanding the geological history they represented. Voyager 2 followed in July 1979, adding more imaging data and refining the picture. The Voyager encounters with Ganymede lasted only hours. The spacecraft were traveling too fast to slow down and enter orbit. They were using Jupiter's gravity as a slingshot to continue outward to Saturn, Uranus, and Neptune. But in those hours, they transformed Ganymede from a point of light into a world. The Galileo spacecraft arrived at Jupiter in December 1995 and spent nearly 8 years in the Jovian system until September 2003, when it was commanded to plunge into Jupiter's atmosphere to avoid contaminating the moons. Galileo performed 6 close flybys of Ganymede during its mission, approaching as close as 835 kilometers from the surface. During those flybys, the spacecraft's magnetometer detected Ganymede's intrinsic magnetic field, the first detection of a self-generated magnetic field around a moon anywhere in the solar system. The discovery was unexpected. Theoretical models before Galileo had suggested that Ganymede's interior should have cooled enough to solidify the iron core, shutting down any geodynamo. The detection of the magnetic field showed that those models were incomplete, that something in Ganymede's interior was still generating and sustaining the field, and that the interior was more active than anyone had predicted. The discovery of Ganymede's magnetic field is one of the most significant results of the Galileo mission, and it remains unexplained in full detail today. JUICE will measure the field with precision that Galileo could not achieve. It will constrain the core properties that are required to sustain it. And it may, finally, tell us why a moon this size still has a functioning geodynamo when the model said it should not. In 2021, the Juno spacecraft, primarily a Jupiter orbiter studying the gas giant's atmosphere and interior, made an opportunistic close flyby of Ganymede. On June 7, 2021, Juno passed within 1,038 kilometers of Ganymede's surface, the closest any spacecraft had come to Ganymede since Galileo. Juno's instruments, though not designed specifically for Ganymede's science, collected useful data during the flyby. Its microwave radiometer probed the upper layers of the ice shell. Its ultraviolet spectrograph observed the surface composition and the aurora. Its magnetometer added new magnetic field measurements. The data from the Juno flyby provided a useful preview of what JUICE will see in much greater detail, and raised some questions of its own, including observations of the aurora that differed slightly from the Hubble predictions, suggesting that the magnetospheric interaction between Ganymede and Jupiter is more dynamic than previous models had captured. Science is like that. Every measurement answers some questions and raises others. Every mission reveals details that no model predicted, and those unpredicted details are often the most scientifically valuable. JUICE will encounter the same. It will arrive with models built from Galileo, Hubble, Juno, and decades of theoretical work. It will measure what is actually there. And what is actually there will be different, in ways both small and significant from what the models predict. That is not a failure of science. That is how science works. The model is refined. The understanding deepens. The question sharpens. You sit on the grooved surface and look at Jupiter. 400 years of observation. Galileo's handmade telescope. Laplace's equations. Voyager's cameras. The Galileo spacecraft's magnetometer. Hubble's spectrograph. Juno's flyby. JUICE somewhere in the dark between Earth and Jupiter. All of it aimed at this moon. All of it trying to understand what is here, what is really here, beneath the surface, beneath the ice, in the ocean and the rock and the iron core, in the magnetic field, and the aurora and the gravitational field, and the orbital resonance. The understanding has grown enormously in 400 years. It is still incomplete. It will still be incomplete after JUICE. There will be questions that JUICE raises but cannot answer, and those questions will motivate future missions, missions not yet designed, not yet funded, not yet launched, that will push the understanding further. Perhaps eventually, a mission will be designed to penetrate Ganymede's ice shell directly. Not in the near future, the technical challenges of drilling or melting through 150 kilometers of high-pressure ice are extraordinary, far beyond current capability. But the scientific motivation is clear. If the ocean can be reached and sampled, if a probe can be sent through the ice and into the water, the question of chemistry and biology could be answered directly. Not inferred from aurora measurements. Not modeled from gravitational data. Measured. Directly. The answer to whether Ganymede's ocean contains life, or contained life at some point in its history, or has never contained life, is physically present in that ocean. It exists. The information is there. It is simply not yet accessible. That gap between knowing where the answer is and being able to reach it is the gap that defines the current frontier of solar system exploration. It is not a discouraging gap. It is a map. You stand up from the ridge where you have been sitting. The grooves stretch out in every direction, ancient and parallel and still. Jupiter fills the sky. The Laplace resonance keeps its time below you. The ocean moves slowly in the dark between the ice and the rock. The aurora glows invisibly in the ultraviolet above the poles. And somewhere in the space between Jupiter and the Sun, JUICE is traveling. Its solar panels are extended. Its instruments are in their cruise configuration. Its trajectory is calculated. It is going to arrive. There is something steadying about that. In the scale of Ganymede's history, 4.5 billion years of orbiting Jupiter, of being shaped by tidal forces and bombarded by impacts and cooled from the inside out and frozen at the surface and yet kept liquid beneath, the 8-year travel time of one spacecraft is an instant. Less than an instant. An unmeasurable fraction of this moon's age. And yet the arrival of that spacecraft will change what humanity knows about this world in ways that 4 centuries of observation could not. The size of a thing is not always measured in years or kilometers. Sometimes it is measured in what becomes knowable. The sun is low on the horizon from where you are standing. It is always low here, always thin and cold and distant. The light it casts is pale and directional and precise, raking across the grooves and throwing long shadows that make the terrain look almost architectural, as if the grooves were built rather than formed, as if something intended them. Nothing intended them. They are the consequence of physics. Thermal contraction and tidal stress and crust extension and material welling up from below along fault lines. These are the forces that made the grooves. And yet they are extraordinary in the raking light. Parallel ridges and valleys running for hundreds of kilometers, carved by forces that ended 2 billion years ago, preserved perfectly in the cold. You walk along one of the ridges. Your footsteps leave no sound in the near vacuum. The surface beneath you is cold enough to shatter glass. The ridge is perhaps 200 meters above the groove floor beside you. The scale is vast. The groove floor is smooth, smoother than the ridge top, because the material that welled up from below during the extensional phase settled here in sheets, flooding the valley floor with fresh ice that has been undisturbed for 2 billion years. The only disturbance in that smooth floor is a single small impact crater, perhaps 10 meters across, fresh-looking by Ganymede standards, its ejecta fanned out in a subtle ray pattern across the valley floor. Fresh-looking, but still tens of millions of years old. That is fresh here. That is recent by the standards of this world. You walk the length of the ridge, and the groove runs beside you the entire way, parallel and precise, as if drawn with a straight edge across a surface that was momentarily fluid and then froze in place while the straight edge was still there. In a sense, that is exactly what happened. The tectonic extension that created this groove pulled the crust apart along a fault zone that ran for hundreds of kilometers, and material welled up along that line, and the motion happened over millions of years, in a process too slow to observe directly, but too large to miss in its result. Geology is a slow science. Its subjects do not perform for observers. They simply accumulate, and the accumulations become readable to those who learn the language. The language of Ganymede's surface is one of the most complete geological records in the outer solar system. Every feature has a story. Every story has a timestamp, and the timestamps, read together, tell the history of a world that formed violent and hot, that cooled and organized itself into layers, that stretched and cracked along its surface in a period of geological activity, and that has been quiet ever since, patient in the way that only geological things can be patient, on timescales that make human patience seem like impatience. You stop walking. You have reached the end of the ridge, where it dips back down into a junction with another groove system running at a slight angle to this one. The two groove systems intersect here, and the intersection is a complex jumble of ridges and cross-cutting fractures, the record of two separate episodes of extensional tectonics superimposed on each other. Whichever system is cut by the other is older. The one that cuts across is younger. Reading the cross-cutting relationships at this junction, a planetary geologist could determine the relative age of the two groove systems, which came first, which came second, separated by perhaps 100 million years of geological time. You look at the intersection for a long moment. Then you turn back along the ridge, walking slowly toward the place where you started. Jupiter watches from above. You sit down on the ridge facing Jupiter, and you stay still. There is nowhere else to go. There is nothing else to do. The universe does not require anything of you right now. Ganymede does not require anything of you. The ocean below does not require anything. The geodynamo does not require anything. You can simply be here, in this moment, on the largest moon in the solar system, with 4.5 billion years of history below you, and the future arriving slowly from the direction of the inner solar system. The cold is constant and even and total. The silence is the silence of a place that has never heard a sound. Jupiter's bands shift slowly in the amber light. A small moon, Io perhaps, or Europa, is visible as a bright point near Jupiter's limb, moving in its orbit, keeping its resonance, doing what it has always done. The stars are out, behind Jupiter, behind you in every direction, fixed points of ancient light, each one a sun, some of them with planets, some of those planets with moons, some of those moons with oceans, the galaxy enormous and ongoing, indifferent and magnificent. You are very small here. You are on a moon that is orbiting a planet that is orbiting a star that is one of approximately 200 to 400 billion stars in the Milky Way, which is one of perhaps 2 trillion galaxies in the observable universe. The smallness is not diminishing. It is clarifying. When you are this small in a place this vast, the things that feel large in ordinary life, the pressures and urgencies and worries that fill ordinary hours, become for a moment measurable, proportional. Ganymede has been here for 4.5 billion years. The ocean has been dark and pressurized and vast for 4.5 billion years. The magnetic field has been turning for billions of years. And all of it, every layer, every orbit, every aurora, will continue long after every concern you carry tonight has resolved itself one way or another. The universe keeps its own time. The Laplace resonance keeps its own time. You breathe. You let your weight settle against the ridge. The ridge is solid. It has been solid for 3 billion years. It will be solid for billions more. Jupiter turns enormous and unhurried above the horizon. The stars are very bright in the absence of any atmosphere to scatter their light. You have been to the surface of Ganymede. You have crossed the magnetopause and watched the invisible aurora rock above the poles. You have descended through 150 kilometers of ice and into the dark ocean below. You have traveled backward 4.5 billion years to the disk of gas and dust where this moon was assembled. You have traced the history of its surface, the bombardment, the rifting, the grooves, the silence. You have stood in the gap between what is known and what is not yet known, and you have felt the shape of that gap. You know this world now. Not completely. No one knows it completely. But you know it in the way that science allows knowing, not by touching or tasting or hearing, but by measuring and inferring and reasoning, by following the chain of evidence wherever it leads, by sitting with uncertainty where evidence is absent and not filling that uncertainty with guesses. Ganymede is the largest moon in the solar system. It has a magnetic field that no other moon has. It has an ocean larger than all of Earth's oceans combined. It has been orbiting Jupiter since before the Earth had a solid surface. It will be orbiting Jupiter long after the Sun becomes a red giant and the inner planets are consumed. It has given humanity one of the most elegant proofs in the history of planetary science, an ocean inferred from the rocking of invisible auroras, measured from a telescope in orbit around a planet more than 600 million kilometers away. And it is waiting, patiently, in the way that only something 4.5 billion years old can wait. For juice. For whatever comes after juice. For the answer to the question that has been sitting in its dark ocean unanswered since long before there were any beings capable of asking it. You close your eyes on the ridge. Jupiter is still above you, even with your eyes closed, its reflected light through your eyelids, its gravity imperceptible but real, pulling at you with the same force that pulls at the ocean below. The Laplace resonance keeps its time. 1 orbit of Ganymede, 2 of Europa, 4 of Io. The mathematics is perfect. The cold is even. In, out. Let the weight of the ridge hold you. Let the silence of Ganymede hold you. Let the scale of this place, the billions of years, the millions of cubic kilometers of ocean, the vast rolling bands of Jupiter, hold you. There is nothing required of you here. Only this. Only now. Only the slow and perfect turning of the solar system, and the ancient moon beneath you, and the dark ocean below that, and the iron core below that, and the magnetic field rising upward through all of it, and out into space, invisible and ongoing. You are not required to understand everything tonight. You are not required to resolve anything. The universe has been working on these questions for 4.5 billion years and is not finished. You can set yours down for now. The grooves will still be here. Jupiter will still be here. The ocean will still be here. In the morning, or whenever you next open your eyes, Ganymede will still be there, visible if you know where to look, as a tiny point of light near Jupiter in the night sky. Not a point of light anymore. A world. An ocean. A magnetic field. A moon in orbit for 4.5 billion years. Understood, partially, carefully, incompletely, by the slow accumulation of observation from very far away. If this is the kind of story that brings you here, please consider subscribing to Quiet Science at Bedtime. Leave a like if Ganymede stayed with you tonight. A notification means you will hear the next story when it arrives. These episodes take a long time to make, and every subscription and every like is what makes the next one possible. Thank you for being here. Thank you for listening. Good night. Everything you heard tonight is real. Ganymede is out there right now.